There we go. All right, so this project is part of the toolbox for research and exploration called TREX, which is in itself a SSERVI node. The purpose of TREX is to decrease the risk for future missions by improving operational efficiency and science yield. Can everybody hear me? TREX focuses on spectral characterization of fine particulates and the potential resources that they may harbor, as well as automated exploration of fine-grained surfaces. There are 4 themes to TREX. The first one being laboratory studies, spectroscopic studies going from the UV to the mid-infrared of fine-grained particulate surfaces. The second one, basically lunar data analysis studies, followed by small body data analysis studies. And the fourth one are the field experiments. So this is the one we discuss, and we're focused on delegating mission planning, data collection, analysis, and decision-making to an automated robotic explorer. And I'll talk a lot more about that in a minute. So here's the concept. Today's robotic exploration is actually centered around a tight operator-robot iterative process, which a team of operators command a robot with very carefully designed instructions. The rover performs them, returns data to the Earth, and you have this iterative process. So here we're basically requesting a full panorama in single filter because there's not enough data bandwidth to do a full color. So robot returns panorama. Then everybody gets together and starts analyzing data. And then, is there a way to point? Oh, weird. Anyways. And then they get together, have a team telecon to decide what is the next step. So the problem is that the data rates are slow, right? You cannot have a complete assessment of the field area, and activities are decided based on very limited knowledge of the site. So here, let's acquire color data of a few places. So basically, because they're data limited, those little squares over there are the few places where they can actually do the data collection. So the robot collects the data, sends it back to the Earth, and once again, we have the whole iteration, and so on and so forth. Oh, look, there's something in that outcrop, a little color variation, let's go there. And it just goes on and on and on, and every single step is very controlled. So we propose a different paradigm, and this comes from trying to explain to people what we're doing here. I usually go, you know, like in the movies, you have this rover that goes and explores everything, and then comes back to the scientists and gives them all this information. They're like, yeah. Well, we're nothing like that. We're literally joysticking our robots around. And everybody's really disappointed. So, you know, let's not get these people disappointed. Let's start a new paradigm. Here, in this paradigm, the rover activities are not uniquely prescribed by each iteration of commands. Instead, the commands are open-ended and responsive to ongoing observations, even without iterative feedback from an operator. In other words, the robot makes its own decisions. This is how it works. So the scientist provides the rover with a set of hypotheses and associated measurable observables. The autonomous rover performs the reverses and observations based on previously acquired knowledge and assesses the terrain on the context of these hypotheses. And periodically, the rover calls back to the Earth and basically tells them what it's found, basically. It gives them a summary of what is found, perhaps images and spectra of the most representative terrains that it's encountered, and so on and so forth. And sometimes, if the rover encounters something that was not expected, something having, for example, a spectrum that is not in the spectral library, it stops and calls Earth and presents them with the new data. And so new discoveries are made. So this is basically the iteration. It starts, how do you point here? Does this work?
There should be a bright spot. We're getting a new.
Huh?
A new one.
That's all right. Okay, so it starts with the top left. The scientist provides basically a hypothesis map, a bunch of pool of hypotheses. Then the next step is basically the path measurement plan. Here the robot decides basically does a data optimization problem on what pathway it will take throughout the terrain to acquire all the data necessary to address these hypotheses. There can also be explicit commands from the ground telling it you cannot go there, please start going there, and so forth and so forth. Then the rover starts, executes the observations, then basically maps the probability weights, and we'll discuss that in a second, and then returns with the information to the Earth. It returns the information to the Earth only. So for example, the robot could have a mineralogical map. Here's a map of Arches National Park on the left, and it's a mineralogical map of the same park taken by Everest. So the rover would have this in his mind, right? And the field of study is somewhere up to the north in that area where there's a lot of color variation. So we tell the rover, go explore that area, return the most representative spectra, minerals, and associated images or other measurements. Like tell us where to collect samples from, for example. So basically, the rover has this information. It can also have other forms of information. For example, it can also know what the topography is, so it doesn't get into trouble and fall off a cliff. So in this case, all the red areas would be places that the rover cannot go to. And it decides that on its own, in principle. So there's two primary advantages to this method. There's improved operational efficiency. You don't really have this continuous cycle, iterative cycle. The hypothesis maps communicate the latest objectives simply and intuitively and define what's going to happen next. And you have improved science return. The data acquisition and analysis is not limited by bandwidth. In other words, the rover can go along, stop anywhere at once, take a full panorama with a spectrometer, analyze it, decide what it wants to do, keep on moving, do principal components analysis, find the most relevant spectra, whatever data analysis technique you want to teach it, and it keeps on going towards the different targets that it has decided to go to. It also identifies unexpected compositional targets. For example, you gave the robot, this is a terrain that should be a marine environment, and you should expect to see clays and sulfates, so on and so forth. And the rover's going and doing this little thing, and at sub-pixel resolution, it runs into serpentine, a hydrothermal product. Well, it stops, calls Earth, hey, I found something new. Things like this would be missed by a rover by the way we're doing exploration these days. So the tools we use are the hypothesis map, which I just described. So I'm not going to go very deep into it. But basically, you present a set of hypotheses to be explored and the observables. The rover queries the terrain. Certain hypotheses become weighted towards greater likelihood. Others are eliminated. And in conjunction, the rover populates an n-dimensional parameter space of the observables, allowing to map the spatial distribution of compositional n members, for example, which can then be targeted for more in-depth analysis. So in communication, as I said, occurs at points in which the rover has a summary of observations, identified sample collection sites, or performed an observation that cannot fit into the hypothesis map. And if the latter occurs, we enter the cycle where the scientists develop new hypothesis maps to accommodate to the data that they can now have, and the cycle continues. The other tool is called Tetracorder, which is an automated spectral identification tool based on an expert system. 2 minutes? Okay. Well, it does feature matching in a spectral library to identify features. It's very powerful, and it's been used all over the Earth and other planets for exploration. So in the field campaign, basically, we're going to use spectrometers from the UV to the mid-infrared and a gamma ray and neutron spectrometer with active interrogation. The rover we're going to use is called Zoe from Carnegie Mellon, which is pictured here. It's very capable. Anywhere a mountain bike can go, this rover can go. We have about 4 weeks total over 2 years to go in field sites. And the field work will be in places where we have fine-grained environments. So for example, here's the Hopi Buttes area, where we identified several locations we could target. For example, in one location, we have erosional windows into layers deeper down. In another one, we have more of the same, but variations at different scales. For example, we also have contact between volcanic lava flows and underlying sediments. We have the actual buttes that also overlie interesting sediments. And we have basically fissure eruptions. Yellow Cat is the same. You can see from this image just the amount of color variability taken from a drone. On the left is a road for scale. So there's a lot of variability in a small scale, which the rover can explore. So the operational scenarios we are comparing are basically the standard paradigm, an astronaut and a semi-autonomous rover and the autonomous rover. And we want to compare the science yield and operational efficiency. So we're going to have a remote science team, which is basically prepares the hypothesis maps and prepares the different science operations. And we have the on-site operations team. In the astronaut rover scenario, we can have two types of scenarios. One of them is a short sortie, where the rover is actually does the same thing I just described, basically interacts with the scientists to respond to the hypothesis map, and then the scientists contact the astronauts and tell them where to go, so the astronaut doesn't have to spend too much time out of base. Or the long sortie, where the astronaut actually behaves like a geologist and the rover walks around like an instrument caddy. So anyways, I'm gonna leave this up, but basically the metrics are that we're still working on them, but elapsed time would be one of the metrics for operational efficiency, and the science yield, basically how much data do you accumulate and respond to new discoveries. And that's it for now.
We got time for a few questions.
Yeah, I'm curious, the decision cycle you showed was more like a Mars decision cycle, right? Where you have a telecon and it's very long. But when you're at lunar distances, you can have decision cycles that are seconds or under a minute. Have you considered that in your planning for comparative purposes?
The decision cycles, of course, there's light travel time, orbiter, relay time, and so on. But there are also decision cycles that are based on analyzing the available data. You get to a location and you have many options of what you're going to do. You're going to stop with your team and you're going to analyze the data before you just go off and joystick your rover, down a slope, for example, or select some outcrop to go to. You're going to stop. You're going to decide. You're going to iterate. Then you're going to tell the rover, drive 10 meters this way, or you're going to joystick the rover over, and so on. But yeah, I mean, the operational efficiency is going to vary depending on the planetary body. But say, for example, we go to Ceres.
Just curious.
Barbara Cohen, NASA Goddard. How are you going to, I know your metrics aren't done, so I'm not asking you to tell me the metric, but how are you going to compare those metrics to the truth? What is your truth?
So for elapsed time, it's pretty straightforward what the truth is. It's a comparative thing, right? Basically, how long did it take?
I don't mean that. I mean your hypotheses. The area that you're investigating, what is right about it, and how are you going to know how right you are with your different your different methods of approaching it?
So the question of whether it's right or not, I would like to say that is not as heavy as the question of how much of the data, how much science you were able to accomplish given the same amount of time and resources, for example. In other words, were you able to discover the same kind of sub-pixel resolution layers, or the random little over there I'm holding a piece of opal that I found in a large carbonate deposit, which basically was all opportunistic science things, and those can be used as metrics to define which one is actually getting the highest science yield.
So just as a comment, one thing that we found in our field work is that sending out a Tiger team or some other team of just highly trained field geologists that are going to get closest to the truth with the methods we know as geologists is something that you can benchmark and use to compare these methods that you're talking about.
Yeah, and that's a great idea, and we have already done the scouting part of that you just described here. But
So you've already done the scouting.
yeah, but
How many people on your team know what it is already?
me?
Well, okay, so that's what I'm saying is, having a Tiger team that goes out and has the same amount of time and has the same metrics as you're using, right? You've had a lot of time to look at integrated data sets and whatever. So having a team that works on these time scales and does exactly what you're asking your other team members to do, but has field geology knowledge is something that it's just helpful. It's just a thought.
Yeah, no, I appreciate it, and we're definitely going to include that.
All right, great. Very good.